Let's practice another transient analysis problem, and in this case we're given a gigantic container of air attached to a much smaller container over here. The idea is that the small container on the left, which has a volume of 2 cubic meters, is so much smaller than the huge reservoir on the right that by putting the two into contact and turning that valve so that air can actually flow from the big container to the small one, we're not going to be able to change the global properties of the big container. An extreme version of this that you could imagine is if you open the window to your house. Of course, the atmosphere outside your house can change the temperature or the air pressure inside your house, but surely your house was not so hot or so cold that suddenly the air temperature outside changed as a result of you opening your window. Your house is the much smaller system. That's the part where you notice changes. Okay, so the conditions inside this large reservoir to the right are going to be that there's a temperature of 300 Kelvin and a pressure of 10 bar, and it is air. The conditions that we're trying to achieve in the leftmost container are that we turn this valve, and as we do so, we let air into the container on the left until we hit 310 Kelvin and 4 bar. So when we hit that temperature and that pressure, we turn the valve back so that no more air can flow in. Obviously, if you let the system just interact indefinitely, you would expect on the left-hand side for the small container also to be at 300 Kelvin and 10 bar. We've stopped it before that can happen. So we have ideal air flowing into a rigid empty container on the left. Empty means initially empty. We're allowed to ignore kinetic and potential effects. Well, that should simplify our lives a little bit, and we're told that the valve closes again at the conditions of 4 bar and 310 Kelvin in the left container. We also need to specify that it's a really large reservoir on the right-hand side so that we know the temperature of 300 Kelvin and the pressure of 10 bar are maintained. You may also have noticed that I subscripted those two quantities with a letter I. That's for inlet. So that means that the temperature and pressure at the inlet attached to our system over there on the left are those two values. Okay, we know it's a large reservoir, so we don't need to see it. I'd like to get that out of the way so that we can write some stuff there, so I'm going to erase that and just keep the temperature and pressure at the inlet. Okay, so let's try and figure out first how much mass enters this container on the left. To do that, we'll use the general conservation of mass that's applicable for transient systems. And that is that m at some time t minus m at t equals 0 equals the difference between the total amount of mass that has come in through an inlet and the total amount of mass that has exited the system. Well, in this particular circumstance, much as in our previous practice problem, it was initially empty, so that means that MCV at time equals 0 is also 0. And we didn't have any exits. There's no outlets at all, so it's all just air flowing into our container. That tells us that M sub E is 0. So MCV at some time t is the total amount of mass that has gone into the system. In this case, to figure out M sub I, though, we're not going to do an integral. We don't know what integral we would do. We don't have a specified mass inflow rate. You can't just assume that it's constant. But fortunately, we do have an ideal gas, so we're assuming that the air that we're dealing with here is ideal air, and we know its temperature and pressure inside the volume. In fact, we know the volume too. Those three variables should be enough to get us the mass. I'll prove it to you. We can use P big V equals mRT. So we know P, we know big V. We can figure out the gas constant for air. We know the temperature. We can solve for M sub I. So let's rearrange to solve for M, and we'll remember that M sub I and M at some time t are the same. So all we're solving for is the total amount of mass that has gone in to fill this container. So we rearrange to solve for M, see that it's PV over RT. We can rewrite R as R bar divided by M, so that becomes M equals PVM over R bar T. Now we can just plug in the values, right? We're given all of these things. You can look up the molecular weight for air, which is 28.97 kilograms per kilomole. Make sure you put R bar in the right units so that you don't have a random factor of 1,000 floating around. Do all of this, and you get that the mass inside the container after it has been filled is 8.99 kilograms. So we've totally filled it up with almost 9 kilograms of air. Okay, we'll put that number over on the left just so we don't forget. The mass inside the filled container is 8.99 kilograms. And let's erase all this work. Now we want to figure out what the heat transfer is between this container and its environment. We don't really care about whether the heat has been transferred to the big reservoir or to the air around it or some other conducting medium. We don't know, we don't care. But we can compute the total amount of heat that has been transferred using conservation of energy. So let's do that now. My claim is that we can use a dramatically simplified version of the conservation of energy equation for a transient system namely that the change in internal energy is Q minus W, and then these terms involving mass and the specific enthalpy. So how do I justify using this equation? Well, one is that we can ignore kinetic and potential effects. That automatically means that delta E total becomes delta big U, right? Because you can get rid of delta KE and delta PE. Likewise, on the right-hand side of this expression, any terms involving V squared or GZ go away because you can ignore kinetic and potential effects. So that's pretty helpful. We also employed another simplifying assumption, namely that the value of H was approximately constant for the entire process. I'm not worried about the term involving HE. There's no exit, so we're going to set that to 0 shortly. But what about the term involving HI? Well, if we have a constant temperature and a constant pressure at our inlet, as I claimed as a result of having this big reservoir, that means that you can look up H sub I in a table, and we'll do that shortly. If you can look it up in a table, it must be a constant value. Okay, so what terms can we get rid of here? Well, it was initially empty, so there's no initial internal energy. UCV at time equals 0 must be 0. Likewise, the container is rigid, it's not getting pushed around or changed in volume. That tells us that W sub CV is also 0. Finally, we said there's no exit, so ME times HE was there for completeness, but obviously it's going to be 0. So this simplifies our lives greatly. We now just have that U at some time is QCV plus MI HI. Okay. So now I said we were going to look up that specific enthalpy H sub I. We're going to need that. You look it up in the table in the back of your book, table A22. That's where I got this value. H sub I equals 300.19 kilojoules per kilogram for ideal air at that temperature. All right. So now let's simplify our conservation of energy. UCV equals QCV plus MI HI. Ultimately, we want to solve for the heat transfer, but we don't actually know the total internal energy, so maybe we should write this in terms of the mass times the specific internal energy on the left side. Okay, we'll do that. Now the nice thing is, you can use exactly the same ideal gas table to look up the value of little u. You have to be a bit careful, so little u corresponds to the conditions inside the container. So the entry that you would want to look up would correspond to a temperature of 310 Kelvin, not a temperature of 300 Kelvin, which is just the condition at the inlet. You have to be careful and make sure you get that right. But if we look in the table, we see that U sub CV is 221.25 kilojoules per kilogram. Okay, now let's rearrange our conservation of energy expression to solve for Q because we know all the other stuff. So QCV equals M times the quantity, U minus H, and we know all of those values. We already computed M at the beginning, it's about 9 kilograms. We have the values of U and H, we take their difference, and we find that Q sub CV is minus 710 kilojoules. So the heat transfer is negative. That means that energy has been subtracted from the system by heat. That's odd. So we had gas going from a container that was 300 Kelvin, moving into a smaller container where it was hotter, 310 Kelvin, and the claim is that we actually lost energy from the system through heat transfer, and quite a bit, 710 kilojoules lost. What's going on here? What's the source of heat? Well, actually, it's something that we accounted for automatically. We should all be thankful that we did it this way. It's caused by the flow work. So if you remember, the flow work involves the pressure at some interface between your system and the environment. Well, in this case, when we first opened that valve, the pressure in the reservoir was quite high and there was zero pressure inside our container. That caused a very large force to move a whole bunch of gas into our little container. That delivered a whole lot of energy, and some of that energy ended up as heat in the form of an increased temperature. A lot of the other energy that ended up as heat had to be transferred away. So the environment somehow heated up as a result of this process. That's kind of a typical result for filling an empty container. You end up having something that heats up dramatically unless you get rid of some of that heat energy, and it's all attributable to flow work.